Should we start then?
Yes, sir, we are good to go.
Okay. Good. So from our last day's class, we know about modular arithmetic. Remember? We know about we have learned about modular arithmetic. We have seen that how modular arithmetic can works with a different dials, right? In fact, the clock we use is nothing but a modulo 12 calculator. And we know the properties of a prime number. We know how to factorize a number. We know how to divide a number. We know how to multiply a number. These are the basic things we know. Now we are talking about something trapdoor function. Today only we discussed about something called trapdoor function. That means multiply one way getting the output of that function is easy, but reverse is not impossible, but very hard job. That is called a trapdoor function. So if I know some information about that function, then it's very easy easy to find that function. But if I do not know those information, it's very difficult. One of the trapdoor function is multiplying. Multiply is easy. I can multiply any two big number and it's easy for us to calculate. Like if you just take two very big number and multiply with a simple calculator, you will get, or even manually also you can multiply. It's easy. You can do that. And with a calculator, it is just super easy. You can get the answer. But if I give that multiplication result and ask you, hey, what is the factor of this number? Yes, we can get that two numbers back. It's possible, quite possible. But it's very difficult. The only way to do that is kind of a brute force. Like first we have to check whether this is divisible by 2, then we have to check whether this is divisible by 3, then 4, then 5, blah 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 blah. And in that way we usually find out the factors. That's the only way we can factorize. But multiplying is easy. Just take two number and multiply. But factoring is not. That's why this is a very good trapdoor function. Understood, everybody?
Yes, sir, we got it.
Okay. Now let us quickly touch upon the modular arithmetic once again. Last day we learned that A by B equals to quotient with a remainder R, right? That means if I divide A by B, there will be an answer quotient Q and the remainder will be the R. And R, probably from our childhood, we never gave any importance to this remainder. Rather, whenever we get a remainder during a division, we said, oh, again a remainder. We never give enough how to this remainder. But today, when we are doing the encryption like cryptography class, probably this is one of the very big factor that or this is one of the very big member that we are giving importance today. Okay. So today, like from our childhood, we never gave it any importance. Today we have to. So this one we can write. I'm just taking my pen here. A B Q and R. And do you remember also we learned this formula? This means A equals to B into Q plus R, right? Do you remember this formula?
Yes, Avik.
Yeah.
So divisor equals to dividend into quotient plus remainder. That's what we learned. Sorry, dividend equals to divisor into quotient plus remainder. That's what we learned. And we can write it in this format also. So this is a format like we can write A by B equals to Q and remainder R. That is one way we can write, or we can write it in a better way, which is called A mod B equals to 3. That means if we divide A by B, you will get a remainder 3. That's a simple thing. This is a 10 modulo calculator. Any dial, the clock dial we use, that is a 12 modulo calculator. This is a 10 modulo calculator. How? Say take any number, say 18. 18 mod 10, what will be? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this will be the 18 modulo 10. This is a modulo 10 calculator. If you get modulo 12, then 18 means, sorry, what I think I made a mistake. 18 means here, right?
8.
8. 18 means here. If it is a mod 12 modulo 12 calculator, then 18 means 6. So in that case, like just imagine a clock dial, and if we just calculate wherever 18 ends, it will be 6 o'clock. We know 1800 means 6 o'clock. You know, in the train timetable or flight timetable, we have always seen. So this is A mod B. And we sometimes write it into this notation also. A, this is called a congruent sign. It's not equals to, it is called congruent sign. A congruent, B mod C. Mod C is not here. This is simple to understand. A divided by B, that means 3 remainder, A mod B equals to 3. It is written in a different way. A is congruent to B when we apply mod C. Why we are calling that? Why we are calling it A congruent to B with mod C? We'll come to that. But this is how the mathematicians loves to write. Mathematicians are never an easy people. They always try to make it more complex, but it is not complex. It is a perfect. That's why they write it in this format. They call it a modulo congruence modulo. Okay. Yeah. In case you remember your discrete mathematics classes from your BTech days, probably you will remember these things. You have already studied the equivalence class, ring, and modulo and congruence. These things are already covered in the engineering mathematics. If you can remember. If you can't, okay, don't worry. Now let us see why we call it a congruent class, or sorry, why we call it congruent, or what is an equivalence class. It's just quick recap here. Say let us take a modulo 5 calculator or modulo 5 dial. Okay, 0, 1, 2, 3, 5. So take any number. If you just keep on counting where it ends, that is the modulo. Now you see, we can actually break all the number. We can put all the number in the universe into this bucket, into this 5 bucket, because it is a modulo 5. That means there all the numbers that is there in the universe. We can put either they will have 0, the remainder will be 0 if you divide it by 5, or 1, or 2, or 3, or 4. Now we write all the number that will have a 0 modulo, like a 0 remainder, and put them in the same bucket. Again, when all the numbers in the world that has one remainder 1 modulo, the answer will be 1. If we do modulo 5, they are given in the second bucket, third bucket. So we can create 5 such buckets, and inside a bucket, all the numbers are there. We are calling it equivalence class. Why? Because they're equivalent. When we have a function for modulo 5, if we think about this particular function, for this function, all the numbers in the universe are falling in the 5 different buckets, and all these number in this bucket will have zero modulo, like as will have zero remainder if I divide by 5. So that's why for these functions, these are equivalent. Does not matter. I do not know. Just imagine a situation where we do not have any other function in the world, just modulo 5. That is the only function we have. So all these numbers that is falling in this bucket will have the same values, like will have the same meaning in terms of modulo 5. That's why we are calling it equivalent. That's why 6 is congruent to 26, or they are equivalent to 26 when we are applying the function modulo 5. That's why we are writing 6 congruent to 26 with modulo 5. That means they are falling in the same bucket. Clear? This is what we already learned in our discrete mathematics classes. This is simple engineering mathematics that you have learned. Now, does it refresh your memory, or probably if you feel this is the first time you are learning, then also it's fine. It is clear, right? This is why we write it in this form. So in anywhere, if you any book or any text anywhere, if you just see 6 congruent to 26 with modulo 5, or any other number like m congruent to n with modulo g, you will not get confused, right? You know the meaning. You can read that at least. Now about this, so all these 4 statement has the same meaning mathematically. A congruent to B with mod C. That means A mod C equals to B mod C. Makes sense? If you divide it by A by C, whatever will be the remainder. If you divide B by C, the remainder will be the same. It's the same, right? This is 0, 1, 2. So
Yeah.
all these numbers will have the same remainder. So we write it in this format or this format. Or we can say A minus B is always divisible by C. Can you say that?
Yes, mathematically we can prove it.
Very simple. It's just opening my tab. Say
6 and 26. So 26 minus 6 is 20 is divisible by 5.
that is with the example we can prove, or without even example. A divided by what is C something something Q1 and R1, and C Q2 is also the same remainder. Since they are in the equivalent class, that means A congruent B for mod C. Right? This is what we can read. From here we can see C into Q plus R equals to A, and here B equals to C into R. So, you guys please tell me, help me here.
Uh,
A equals to
A equals to C into Q1 plus R, and B equals to C into Q2 plus R.
right. Now
Yeah.
A minus B equals to C into Q1 plus R minus C into Q2 minus R.
Some
Right?
lag is there. We are not able to see actually.
Okay.
But yes, that is correct.
Now is it coming? Oh,
Session closed.
what happening with this? I knew this AnyDesk is the best one, but it doesn't seem so. Okay. The remote user rejected, no? What does it mean? Once again, any disk.
Hey, are you writing with some stylus or a pen?
Style, actually, it is a Ace pen. So I am using a Samsung tab, and it has a Ace, like it has a this stylus pen.
Then any MS Paint file or Notepad file, or in fact in this screen also you can write, no?
But I need to no, on my computer screen I cannot use this pen.
Okay, okay.
Only on the tab I can do that. I think this is okay. I guess now we get it. Yeah. But I was telling A minus B equals to CQ plus R minus CQ plus R, right? This one and this one. That means RR cancels out. It is Q1 minus Q2 into C. That means if like Q1 minus Q2 are always an integer. If Q1 is, I'm just assuming Q1 is greater than Q2, that means this is an integer. So A minus B will always be divisible by C. Right? Or A minus B mod C equals to 0. Easy to understand? Or I lost all of you? Are you there?
Yes, sir. We can hear you. We are good.
Sorry. I thought that probably my microphone is not working or speaker is not working. Okay. So this is clear, right? Why I said so. So now we understand why C is always divisible by A minus B, and also A equals to B into K plus K into C. K is any integer. That's why this happens, right? If it is an integer, then it is A is always divisible. A minus B is always divisible by C. So these are the equivalent statement. All these four statement has the same meaning, right? Now we never did like never thought about this modulo arithmetic, but if you just try to figure out, you will actually prove all the five properties. A plus B mod C equals to A mod C plus B mod C whole mod C. You can find out. It's very simple. Like A if you divide it by C, there will be a remainder. B if you divide by C, there will be some remainder. If you just do the same for A plus B, you have to just add those remainder, and then again you have to make a mod C, because the remainder adding up might be greater than C. That's why you have to apply another time mod C. It's very simple. You can like with the uh, same way that I have proved it here. Exactly with the same formula that we have learned in class 4 or 5. Using this one, you can actually find out all these. You can actually figure out all these properties. A plus B mod C will be this. A minus B mod C will be this. A mod C minus B mod C whole mod C. A into B mod C will be A mod C into B mod C whole mod C. And just if you think why it is happening, it is very simple. Just in a like it's in the school days class 4 or 5 we have all learned that why it is happening. If A into B we find this one, then we can easily find A power B. A power B is nothing but A into A beta, like B times, right? That means A mod C whole power B again mod C. And if there is a constant, like k into a mod c equals to ka, if you can simply multiply the constant with the dividend, and then you can divide with the divisor. So these are the very simple rules. We probably right now we are learning, but in class 4 or 5, student will also understand that why it is. They will not understand why we are doing that. But yeah, that is understood. That is quite understood. So these 5 arithmetic properties for modular calculus will need very soon. Okay, we'll use these properties. Now, one more thing. Euler was a great mathematician. He worked with the prime numbers. It's long back, like I think some 1500 years ago. Euler was there. No, sorry, not 50. Euler was, I think, in 1400 or 1500 AD. Not much. I was confusing him with Euclid. Okay, Euler, who worked with the prime number, he said if n is prime, then a into b equal mod n will be 1. Then a and b are inverse to each other. That means if two number, if I multiply them and then mod with n, if we get 1, then we call these two numbers inverse to each other. Okay, let us this is a property that Euclid said, but it will not be useful. But just Euclid has two formulas. This is one of them. And the second one, which will be really useful for us, what apart from those 5 properties that we learned here, there is a 6th property that Euler has given. A mod n power b equals to a power b mod n. We can prove this with these five properties. The 5 properties we have already understood. With these 5 properties, we can actually prove it. A mod n power b equals to a power b mod n. But later, for the time being, let us just understand that this happens. We can take a number. We can just examine that whether it is happening, or we can prove the formula. We can prove this formula as well with the other properties. I'm not going detail into that, but this is the formula that we are going to use. A mod n power b equals to a power b mod n. Okay, these are the 6 formulas we will use today. You remember the Diffie-Hellman key agreement. Last day, when we discussed about it, I think where is the last day's class? I think last day we discussed about this thing, right? And we took this number.
Yeah, colors.
Exactly, the colors. And then we explained with some number, right?
Yeah.
Now, there was something that we thought that 2 power 4 equals to 16 is easy to compute, but very difficult to get the reverse. Even though we know the value of 2, other than a log table, it is not possible for us. 4th square root of 16, it's very difficult difficult for us to find, right? That is what we assume, but we have log tables. But we have a lot of other ways to find that. This is not really difficult. It is difficult, but we know how to solve this problem. So this simple power thing is not work. Simple logarithmic function is not working here because we have the log table ready. So what we can do? We can simply add a modulo after this. In that case, it is really unbreakable. If these numbers are very big and then I mod it with another very big number, no log table can solve this. This is kind of putting a hash in the rainbow table kind of things. So we are making a modulo calculus. We are bringing modulo into that. So exactly the same thing we are doing. Here 2 number is generated. This we are calling generator, or like some common number that we have decided that everybody can know. And I have a common number, like Alice or Bob has a common number. Alice has a common number, and I just make this previous number power my number, and I will send it to the other person. And I assume that this is not this cannot be reversed, but it actually can be reversed. That's why I usually write mod something. How it works? Let's see. So I can get a very large prime number and alpha as a generator. Okay. So two numbers instead of one number, we will decide two numbers. And then the message is alpha power this one mod q, and y is alpha power the other secret number and mod q. And from this one, yb is really, it is not possible to find the value of b, or this is not possible to find the value of xa. That's the beauty of this modulo calculus. Okay. Is it clear, or do you want me to explain in a table and whiteboard?
I think with example it would be easy with small prime number.
Okay.
2 and 5.
Okay. For I'm just trying Bob and Alice.
Alice and Bob.
And Abhijit is getting replaced by Alice. Okay. The first number in our example, we first number we take 2.
2 and 3. Take 3. 3 would
So now it's
smaller
also,
prime.
this is also 2. So the first number 2, and everybody I know, like Bob know, Alice knows, and everybody else also know this is a number, first number. Then okay, this is not Shomo, this is Bob's secret. This is now Bob's secret. We in our example we took 4, right? And Alice's secret is 5. He knows. Now Bob's mixed color is 2 power 4. Is the 2 power 4 to 16. This is the Bob's mixed color, and everybody knows this 16. And Alice's mixed color is
Okay. I thought for Diffie-Hellman key exchange we are doing.
yeah. This is what we did, and then I'm just replacing it with the modulo. Okay, just
Okay.
and everybody else know 32. And Bob gets a secret. He knows 16 and he has a secret 5, right? So this is so I will find 16 power 4. I think 4 power 16. This is Bob's secret and this is Alice's secret. So he knows this one, not this one. This is the Alice's mixed color and this is the Bob's secret. And what he will do, Alice's secret 32 power 4. Something, and Alice will find 5. It's the same number. That is what we saw last time. Now what we are doing, we will so this is the one. Now the first number is a prime number. The first number is a large prime number called Q. I'm just taking it as 23, a prime number, right? 23, 20, who knows? I need to add a insert above. This one and insert above. Insert above. The generator is nothing but another number which is called a primitive root of Q. I'm not going into that right now, but yeah, this is something called something called generator. This is called alpha. How can I write alpha? Here. And it is so 5 is a generator of 23. I'm telling what is a generator. File. And Bob's secret number. Just tell any secret number that Bob should have. Anything? Any number? Who is Bob here?
7.
And who Alice, please tell me a secret number for you. Hey Alice.
3.
Sorry, 10. Now what we'll do? Bob will calculate this one. Alpha power x, his secret number with mod q. Let's do that. 5 power secret number is 7 mod 23 17. So everybody will know 17. These guys will also know 17. Now Alice's number is 10, right? Alice, what she will do? The same thing. 5 is the generator. 5 power 10 mod 23 9. Okay. Now Bob has this number. Bob has 7. Bob knows 7 and Bob knows this 9. What we are going to do? We are going to, Bob will calculate a secret like 9 or his own number. What is that? 7 mod 23. And what Alice will do? Alice has Bob's mixed color, which is 17, right? 17 power. Her secret is 10, right? And mod 23. Hopefully it will be 4. Yes. So they will have the same number. Understood? Everybody understood?
Yeah.
It's clear, right? 7 is Bob's color. For your later reference. Say Bob, I'm just representing it as blue. Gold. And this is Alice color, which is something maybe magenta or red. Okay, this is 9. Let's take the mixed color here. Maybe orange. This 9 is used here. This 7. Now is it clear? With the color, this is the 7, this is the 9 it got. And 17 is this color, which I'm just taking another. This is this 17. Now is it fine? For your later when you will see, you will probably this color distinction will help you to understand. Okay, so the secret the for their common secret only.
Yes.
Now it's clear how the different element works with modulo, how it is better than that. Previously we simply skip this modulo part. Now we have created a modulo part. Can anybody tell me why we took a q as a prime number? Why nothing else? Why q is a prime number?
To satisfy the equation, means else they will not get the same key, no?
No, they will get same key, but still we need a prime number. Why? So the q itself is divisible by the generator. We are taking number, right? One q, another is another number. There are two number. If q is itself divisible by alpha,
Yeah.
there will be a problem, right? That's
Problem.
why
Yeah, it should not be divisible.
exactly. That's why it should be a prime number, and alpha is a generator. That means alpha power something will the generate a number which will be in all the possible equivalence class for mod q. Okay, that's why we are calling it a generator. If we take a generator, then it will give a better result. Otherwise, there will be some corner cases where this will not work. That's why they called alpha power something will always will give you the same modulo remainder. That's why we are calling it a generator, because it generates different member of the same equivalence class. Got it? So this is the proof. If we again those properties, if you remember the properties, the sixth, this one, a mod n power b equals to a power b mod n. We are just simply, if we apply that, we'll find that these two will be the same. Y power xa mod q equals to whatever, and y power xb mod q will be the same thing. So if we apply those properties, this can be proved very easily. You can try it anytime. It will work. So this is the with these four properties of the modular arithmetic, you can apply those properties and it will just simply deduct all these things. Now, the Diffie-Hellman solves a lot of problems. It solves a problem for sharing the key, but what will be the problems? But still, does it really solve everything? What will be the problem? Even though we have a Diffie-Hellman algorithm that secretly gives a common secret between two communicating parties, but there might be a problem. What is that? Please tell me, guys.
Whether they are communicating to Alice and Bob itself or somebody else.
No, let us assume that sender and receiver are the legitimate one. They are doing it legitimately, and they are having Diffie-Hellman. They are using Diffie-Hellman for the communication. But still, it might have a problem. What is that?
Yeah, if we keep encrypting the whole data with the same data key, then it is a problem. We need to change it.
But as long as that data key is secret, then it's fine, right? Why do we need that?
Every hour we change the Diffie-Hellman key.
For every session, yes, we can. We should do that, but even if it is not, then also there will be a problem. Even if we don't, because for the substitution and diffusion, sorry, for confusion and diffusion, that is already done by the cipher. So we do not need to do that in the key level. What happens for the OTP that I explained last day? For that, every time we need to change the key because that confusion and diffusions are related with that key. But now we have changed that thing. We have a same key, that is not a problem because that confusion and diffusion is happening inside the ciphers. Inside that, like even I am using the same key, it will always produce different output. So I am fine. Even though I am using the same key, I don't bother because ciphertext will always be the same. Always will be the different. I don't care. So as long as I can keep it secret, it's fine. For OTP, there is no such mechanism. So that's why every time they have to jumble up they have to get a new key. But here for this substitution and diffusion, if it is a block cipher, I'm using S box and P box. That is actually making changing my keys every time. Right. So that's why as long as I can keep the secret, I can keep the key secret, I'm fine. So that's not a problem. Is there any other problem that you see? Anybody? Any answer? Any quick thought? Okay. Bob and Alice are communicating, but it is in real world, it's very unlikely that only two persons will communicate. There will be in cross in communications. So in cross in communications, there will be in cross in Diffie-Hellman key exchange. Are you with me? Yes, no.
Somewhat
Yeah.
50-50. In cross communication in the sense one server is communicating to different clients.
Yes. In cross
Yeah.
in, like in cross in. So there are multiple parties and multiple parties are communicating between themselves. So it is not only Alice and Bob. There are thousands of Alice, thousands of Bobs, and all those 1,000 Alices and 1,000 Bobs are communicating between themselves, creating a channel factorial of number of people. So if there are 10,000 people communicating between themselves, that means there are 10,000 factorial communications are happening. So 10,000 factorial Diffie-Hellman keys need to be exchanged. And everybody, Alice, if he is communicating with 1,000 different person, that means Alice needs 1,000 different keys to keep secret. You are getting my point.
But that we are not doing, no. The key which Diffie-Hellman is generating, we are exchanging through RSA. We are adding one more layer.
Yes, but once I know the secret, so once Bob and Alice knows the secret, they find out the secret, they have to keep that key, right? As long as the communication is happening.
Yes, the data will be decrypted through DH only.
To that DH key, right? Now,
Correct.
Alice is communicating with 1,000 different person. That means 1,000 different keys should be stored, right? Because for everybody here is doing a different key exchange.
Correct.
Now there is not only one Alice, there are some 1,000 of Alices are there. So everybody will have to create so many Diffie-Hellman key exchange, and they will have to keep all those keys with themselves. And all of them are supposed to be in secret. They have to keep it safe, which is very unlikely. Like if I give you one single password, you can remember it very well. But if you have 10,000 password, you have to write it somewhere and it's very difficult. It will be leaked for sure. And secondly, Diffie-Hellman key algorithm involves lot of communication overhead because a lot of messages are just sent in the channel, and also a lot of computational overhead because this something power something and mod, it is a very powerful computation. That means for every communication, everybody will have to go through that overhead, communication overhead and computational overhead. So if it is two persons are communicating between themselves, it is fine. If 1,000 people are communicating between themselves, the Diffie-Hellman will itself eat up half of the bandwidth. Half of the internet speed will be gone for Diffie-Hellman key exchange algorithm only. Then rest half will use the rest half to send our data. Now you've got the problem. Now imagine all the websites in the world and all the clients in the world are doing this Diffie-Hellman key exchange algorithm for every communication, for every session. In that case, half of our internet bandwidth will be gone just for Diffie-Hellman algorithm, and half of our computation power would also go. Right? You are with me? Or still there is doubt? But
Yes. So with only Diffie-Hellman, it is not possible.
yes, only with Diffie-Hellman it is really very difficult, because Diffie-Hellman works well for communication between two parties. But if it is the communication is happening with thousands or millions and billions of different parties, Diffie-Hellman is not useful, because n cross n communication is happening. That means factorial n number of Diffie-Hellman key exchange are happening in the network, which is huge. And we cannot do authentication and signatures. We cannot do with the Diffie-Hellman, because signing a key is not possible. Signing something is not possible.
Not
right?
possible. Correct. Yeah.
But still, Diffie-Hellman key exchange are used in SSL certificate during establishment of the initial session. Not always, but some of the cases. Not always. I am opening a website. That means it is there is having a Diffie-Hellman. Usually, when I am opening a secure session, that time only there will be a Diffie-Hellman algorithm key exchange. Not always, and that is only one time during the entire session. Usually with the bank applications and all, where we really need perfect secrecy, perfect, we call it perfect forward secrecy. That time we need Diffie-Hellman. Only when I really need to know that when the client also needs to be authenticated properly. Okay, that's why. Otherwise, we usually limit the number of Diffie-Hellman key exchange, because it's computationally is very high. That's why bank websites, when you log in, bank websites usually take a longer time to log in compared to other login portals. Okay. And even when you are making a transaction, that time also during the transaction system is quite slow, because the key Diffie-Hellman key algorithm is happening. So when you purchase something, then you click on the payment button. When it goes to the gateway, it takes a longer time. But we usually do not understand that much, because there is a OTP and a lot of manual things are happening. It is asking for OTP. By that time, it actually uses the it actually covers that overhead, that delay. But if there is no OTP, like if you do a international transaction without any OTP and all, you will see that gateway is taking a longer time. Once it is done, then also when from that gateway to coming back to the original website, it takes a long time, because of this Diffie-Hellman key exchange. Okay. Okay, and Diffie-Hellman is still used in SSL, in Cisco encrypting routers. All the routers, they usually mostly the BGP routers by Cisco, they exchange the Diffie-Hellman key between themselves. In fact, Sun has a secure RPCs, like Sun computers. I have not seen whether you have seen that Sun PC. It was there long back when cloud was not there. Sun systems was very popular. Sun Solaris. Okay, so now Diffie-Hellman is also clear for us, and we know the mathematics behind that. Now let us come to the asymmetric key cryptography with the same line. We'll use the almost similar things for the asymmetric key cryptography, what we have learned so far. Here, we need two different keys. One key is for encryption, another key is for decryption. So you remember this kind of locks? Like if you just press it, it can be locked, but if you want to unlock, you need a key. So this idea actually came not only from the mathematicians, it actually came from a very nice novel, English novel. I just forgot the name. I frankly, I have not read it. It's some 200 years back. Somebody wrote a novel, and that I'm not very familiar with the English of that 200 years back English. It's very difficult. I have not read, but the gist of the story is like that. Somebody is sending some messages, and he's expecting the response. What he sent a box, just a box, which can be locked easily, like this kind of lock. He says, whatever response you have, write it, put it inside the box, put this kind of, I'm sending this key with this lock with you, you just lock it. Only I have the key in the world. You send me back the box, I can open it. Even somebody else get the box, he cannot open it without breaking the key, breaking the lock. Idea is simple. Guys, please interact. Otherwise, it's sometimes I feel I'm losing you.
Yeah.
Or,
Yes, it is correct.
okay, so I'm sending something. I have a lock which I can easily lock. It's a paste lock. I can easily lock that one. And the key, who I am sending it, he or she has the key. So only they can open. So that's the basic idea about the asymmetric key cryptography. And somebody thought whether we can really implement this thing mathematically. So that is the motivation behind this asymmetric key cryptography. Rivest himself said that this is that story actually uh, made him interested to do like to think like this way. That story is the motivation for coming up with this algorithm. Now we know the mathematical trapdoor function. So another good mathematical trapdoor function we have just seen. M power e mod n is very easy to calculate. Anything power e is a number, n is a number, and n is another number. If we know the three number, it's very easy to calculate what is the value. But it is almost impossible or a very hard problem if we know this value, this question mark we know, but uh, uh, we do not know the m, the value of m. So how can we find, like, if we do not know the value of m, just we know the rest of the values, e, n, and c, can we find n? Answer is no. It's very much similar to what we saw in Diffie-Hellman. 2 power 4 mod 23 is easy to calculate, but uh, which power, like, what is the number that like square root of fourth square root of some number mod 23? It's really difficult to find out, right? So we can find the power, but we really cannot find the root. And we can solve the problem with log table, and that's why they have come up with the new idea with the mod functions. Then the log table will not. Now we'll learn one more mathematical function, which is called a total function or the phi function. Let's total function or phi says how many numbers are less than equal to n that does not share a prime factor with n. What does that mean? Say, let us take an example, 8. Phi. For calculating what is the so this is just another mathematical function. How we can find? We have to write all the number between 1 to 8. Now we will see whether if all these number 1 to 8, all the numbers I will write, and then we'll see how many of them are not divisible, like do not have any factor with 8. Is 1 a factor of 8? Yes, 1 is like simple. 8 divided by 1 is 0, so 1 is not the one. Is 2 divisible by 8? Like if 8 divisible by 2, yes. If 8 divisible by 3, answer is no. So this is 1. 4 is divisible by 8. 5 is not. 6 has a prime factor, like 6 and 8 has as a GCD, right? 2 is like 6 and 8. If you make a GCD of 8 and 6 as a factor. Just 7, yes. 7 does not have any factor. 8 does not have any factor. Sorry. 8 is factor of 8, but 1 is not considered. 1 is not a prime number, not a prime, nor a so 1 we will not consider. 1 is anyway always a factor for everything. So 1 will calculate, will consider 1. Let us change the color. 1. 3 is not divisible by 8. Like 3 doesn't have any factor with 8. 6 has a factor with 8 called 2. 7 doesn't have any factor. So how many of these number? 4 number. So 5 of 8 will be 4. Is it clear now? Now you guys please you calculate 5 of 15. What will be the value of 5 of 15? You guys tell me now. 5 of 15. How can I how can I
Okay,
should I write?
I calculate.
Okay. Now tell me which one will be the one. One will always be counted. Second, which does not have a prime factor with 15.
So 2,
2,
4,
4,
6, 8, 7, 8, 9, 11, 13, 14.
Correct? How many of them? 1, 2, 3.
2, 3, 4, 5, 6, 7, 8, 10.
Another one we will do. 5 of 13. And I'm just taking this one. Now tell me. One is always counted. Then, sorry,
All except 13.
well, yeah.
It is a prime number actually.
perfect. So for any prime number, 5 of that prime number will be that number minus 1.
Yes.
But if it is not a prime number, it is very difficult to find. If it is not a prime number, only way to find it, you have to write all the numbers, then you have to check each and everything whether they have a common factor or not. If they have, you have to count them, and then you have to. So there is no other formula. There is no other formula. That is the only way of doing to find factors for each and everything for less than this number. But for a prime number, the beauty is that number minus 1 will be the 5. Nice. Now the trapdoor function is like this. If you know what is the number, whether this number is prime or not, if you can find that, it is very easy to find the phi. But if you do not know whether this is a prime number, then you have to do all of them. You have to count each and everything. Makes sense?
Yeah.
Okay. This is what Euler said. And Euler found one more very nice thing. What is that? Phi function. He again tried to figure out that phi. What are the different properties of phi? So one of the major thing is this, that if p is a prime number, then p minus 1 is the phi. If it is not, we have to factorize each and everything less than that number. Otherwise, we cannot find. But if it is a prime number, we don't need to do anything. Just minus 1 is that number. And he also finds this is multiplicative. That means there is a property. Phi of p and phi of q will be phi of p into phi of q. This is a property he found. How we find like you can actually taste it, like phi of 8 into phi of 15 equals to, like, that means phi of 15 into 8 is 120, right? So that means it is very difficult for us to find, but since we know this is 10 and this is 4, we can easily say it is 40. Because phi of 120 equals to phi of 8 into phi of 15 equals to phi of 8 is 4, 15 is 10. Simple. So far it is simple. Phi function, everybody understood? And the multiplicative property of phi function, everybody understood?
Yeah.
Okay. Just curious, other than Parth and Kruta, right? I'm sorry.
Yeah. Yes.
Okay. Parth and Kruta, nobody is speaking. So rest of the folks are watching Netflix or anything. And Kiran also spoke a couple of times, but nobody else never, and Pranab. But I don't hear from anybody else. Are you guys watching Netflix?
No, sir, we are here.
Okay.
No, sir, we are listening.
Okay. Okay, fine. So far this totem function or the phi function is clear to you. How we can get this thing? Yes, no.
Yes, sir. Yes, sir.
Okay. Now this sounds little bit boring. That why this Euler, who had nothing to do, good for nothing fellow, he had probably nothing to do. That's why he has come up with such a mathematical functions. What's the point of doing that? In fact, it's true. Probably for almost 300, 400 years, nobody understood that why this guy has come up with this phi function. What's the point of having this? And again, not only coming up with the phi function, then also he found some properties of the phi function. So there was no practical use case of this phi function. But until this 1970 or 80, whenever this Rives, Shamir and Adelman came, they first probably used this totem function. And they found a very nice trapdoor function out of this. What is that? That is, if you have two numbers, if you like phi of 77 is 60. It's very easy to find if you know one single logic. What? This 77 is coming by 7 multiplying by 11. 7 and 11 both are prime number. So it's very easy. 7 minus 1, 11 minus 1 equals to 6 into 10, 60. Right? But if you do not know that this 77 is coming up by this 7 and 11, because to find that you have to factorize. It's a little factor. It's a very small number, so it's very easy for us to find. But imagine if we have a very big number, which is a product of two very big prime numbers, then it is very difficult for us to factorize that. It's very difficult for us. And if we try to find out the phi function of that, then if we do not know that these are the prime number that which gives the product of this number, we really cannot find the phi function, even with the best computer we have. Now, let us imagine something at a very big number. It's still small for what we calculate. Let us take a very big number, phi of this number. Can you find this number? Can you find the value of phi? The only way a computer can do is write all the numbers from 0 to this number and then factorize each and every number, which is kind of a computer will take a lot of time, maybe 10 years, 15 years down the line. It will take to break this to find this phi function. But if somebody knows that this is actually a product of two other prime number, then why I don't need even a computer, I can immediately find out. Say if I don't know whether this is right or wrong, but let us assume this is. I don't know whether this is right or wrong, just for our example, I am taking. So these are the two prime numbers, say, per se. I don't know whether they are prime number or whether this product gives this number. Just for, let us assume this is a number and we somehow know that these are the two prime number. If I multiply these two prime number, it will give. Then phi of this number is very. What will be the number? What will be phi of this? Tell me, somebody.
The first number minus 1 into second number minus 1.
Exactly. So 3, 3, 4, 5, 0.
4540.
4, 0. 1, 2, 3.
Copy paste. Do copy paste.
This is the number, whatever it is. It is very right.
Yeah.
So
Yeah.
that great trapdoor function that our RSA key cryptography or the asymmetric key cryptography uses. Now let us come. So these are the three guys: Rives, Shamir, and Adelman. All of them are living and kicking, and they are doing really well. They are three directors of my company. So these guys are these are the guys who come up with the extraordinary solution. Okay, I don't need a we can give you a private key and a public key, two set of keys. The beauty is that you can encrypt it with one and decrypt it the other. You cannot use the same key for encryption and decryption. You need the other key to decrypt if it is encrypted, or if you encrypt with the other key, you need the main key to decrypt. So any one of those key you can use for encrypting, the other one will be used for decrypting. So they published this algorithm in 1977. Now let us do some more mathematics here. You guys are connecting, otherwise it will be very boring if I just explain all the mathematics here. So if you can connect, then only it makes sense. Okay. Now let us see the RSA, how RSA works. Let us take any small number, any big two prime number, P and Q, any two prime number. This is what somebody will take. How computer generates a pair of Okay. This is getting synced. I'm creating one. Okay. I see. So we are taking any computer when we generate a pair of private and public key, how it does. It first generates two prime number, any two big prime number. And the next step is n, or capital, let us write it capital N, equals to P into Q. Now, for any other computer, phi of n is very difficult to calculate. No other computers, unless in my computer or I have created this P and Q, I know what would be the value of phi of n, which will be P minus 1 and Q minus 1. But nobody else in the world, it is very difficult for them to find the value of this phi of n. Till here it is clear, right?
Yeah.
Now, once we get this phi function, we can now, if we use this phi function to create our encryption and decryption key, then we are game. Because I only know the value of this one, nobody else will know the value of this one. Even though you know the value of n, but it is very difficult for the other computer. It might take years to find out this phi of n. But for me, it is not. So the very simple rule is encryption key. E is the encryption key. Is just any number which is not a factor, which is not a factor of phi n. I know the value of phi n, so I have to take any number which is like which is not a factor of this one. So phi n should not be divisible by e. It should sorry. What's happening there? Disk is ready. Even any disk. Okay, is any number which is not a factor of phi n. That means take any number in the world which is, by which you cannot divide phi n. Simple. Phi n is not divisible by any number. Just randomly take any number. And decryption E will be a constant, any integer phi n plus 1 by E. Just calculate this. What is k? Why we need an integer? We could actually use just simply phi n plus 1 by e. That would work for us. But the problem is, in that case, this decryption key might be a fraction. I don't want that. That's why any k. So that like we should choose this integer in such a way that this will be an integer. This will end up with an integer number. That's all. Now you must be thinking where this formula came. Like E is fine. I take any number which is not divisible, which is not a factor of pi, and that is there are thousands of such numbers. Fine, no problem. But how this particular formula came, right? But before that, I will come to that how this formula came. Before that, I just want to show you that how this works. Like, let us take a very simple example. Say P is taking this one 53 and Q is 59. Both of them are prime number actually. Both of them are prime numbers. So what will be N? Tell me. Can somebody please volunteer to tell me the value?
Yeah, calculate. $3127.
Sorry,
3127.
3127. So phi of N will be
52 into 58. 3016.
okay. That we know. Nobody else can find this one. Now I take a message. Any
But not visible actually. Your
Yeah,
screen is.
yeah.
okay.
It is
Yeah.
stuck.
Do any other remote desktop tool other than any disk?
Well, you could use TeamViewer, but I don't know how effective that would be.
Sorry,
You could use TeamViewer.
Team Viewer. Okay, yes, Team Viewer I could have used. Okay, during the lunch hour, I will just check. Session is closed, but why I cannot close this thing? Close all the windows. Now this is visible, right? Okay. Now let us take any encryption key which is not a factor of this one. Anything, and just give me any number which is not a factor of 3016.
3015.
That is a too big number. Let us
Too big,
take
no? Correct.
just three. Three is not there. This is not divisible like the
Yeah.
three. Oh yeah. So this is not divisible by three, right? 3016
Yeah.
is not divisible by three. So let us take a simple number three. Okay. And B will be phi of in some k. We have to decide the value of k by 3. So this one I know 3016 plus 1. I have to just find out 3. So we take it here 2.
Again, it got stopped
It
actually.
is against. Okay, now it is coming.
Okay. So this is 2011. This is a thing. So I took the integer as 2 so that it becomes a integer. Right. So this is our encryption key and this is the decryption key. Now let us quickly run this thing with a message. Say a message is 89. Fine. Now the ciphertext will be some encryption function. Encryption of M, which is encryption with E, which is the function is simple. mod n. N we know, and m we know, e we know. So it is 89 power 3 mod
30 or 312.
3127, right?
Yeah.
And let us calculate this one. Actually, from here it is easy to calculate. 89 power 3 89
What's to
89 power 3 mod 3127. Let's see. 1394. This is 1394. So this is our ciphertext. So this is our text. This is our ciphertext. Now when we decrypt, let's see, m dash equals to decryption function using decryption key on the ciphertext. That is 1394 power. Again, we will go to calculate the same thing. This one power this 2011. 2011. Okay. To C power D mod n. That means 1394 power 2011 mod 3127. Let's see. I don't know whether this time one note will work or it will just a hand will come out of the screen and slap me. 94 and 2011 mod
3127.
what did I do know? 2011. Okay, it is. I think it is not able to find out. Okay, a very big number. Let's use Google for this. Even Google is not finding it. No, it's a very big number. Sorry. So the example that we took, I think it's such a big number that even probably we need to write a code to find that. But if we write it, yes, it will work. Okay. But you understood. So
Try
data.
the calculator, scientific calculator. It will work. It is showing 89 as well. Shall I share my screen?
Yeah, please. What I took actually, what I did with the with flow, I took a very big number. So I think we shouldn't have taken 53 and 59. It is a very big number. We should have taken a smaller number. Okay.
12.5 would have been better. Is my screen visible?
Yeah.
So one
Great. Now we are getting the same number. So we can write it. is 89, which is M. So M dash is M. Now the again it got stuck.
Can you share your screen, Soumya?
Yes. Oh, sharing it. Share. So now we understood how this RSA works, right? How the encryption key and decryption key is generated. Now, how exactly, why this is happening, why this formula is coming from? I have shared a note with you. Probably that will help you. I will share that. So in LMS, you will probably find a PDF file. You will get that one, and you will find that how exactly why this formula is coming. Why this is like when we generated the decryption key from the encryption key, why this formula we used, how this formula came from. Probably it is easy for you. So I have uh, done that, and I'm sure I've shared that note with you. So please go through that. I'm not going into detail in this class because we have some other things to cover, right? Action in progress. Okay. I say an elliptic curve cryptography. This is the last thing, and then we'll go for the lunch. Let us see what is the elliptic curve cryptography. So RSA is good, but RSA has a big problem. You understood. RSA's problem is that they are it's simple, but the one problem is the trapdoor function. Yes, it is very difficult to calculate, but it is not under like it's still a good big computer can find it, especially when we are achieving more and more computational power. Someday we will probably very easily break the RSA crypto system. It's not very far. Even though we don't need a quantum cryptography or anything. With a simple computer that we have, the way we are gaining more and more computational power, we'll break it. So that's why nowadays everybody is saying that it's a 1024 bit of key is not enough. We should go for 2048. Probably then we will come very soon. Will come 4096 and bigger key size. But how big you can take the key size? More you take the big, more you take the bigger is the key size. There will be more overhead for the computer keys, right? You have to generate those keys, right? You have to calculate the encryption and decryption. So even the simple one, the simple two prime number of 2 digit, we tried to do that. We could like even the Google calculator we couldn't do. The simple tool that we are using OneNote that couldn't do. Now just think if we are using 40969 right now or bigger key size, it's really not scalable one after some point of time. Yes, it is a very good function, but the problem is we are gaining more and more computational power. So if you have a crypto system and my computer takes 10 minutes to break that crypto system, that means your password is safe for 10 minutes from me. If there is a computer that takes some 10 years to break that crypto system, or say to calculate that phi function, then take your passwords or your messages secured from that computer for 10 years. Now, what we calculate, probably the best computer we have in the world, how much time it would take. It might take. And if it is more than, say, some 1 year or 2 year, then we say, okay, this is reasonably safe. But that does not mean that tomorrow there will be, there might be some other computer which will break it in half an hour. Then the entire system is resilient for that type of computer only for half an hour. Right? So there is a problem. It's a crazily, first of all, it's crazily power consuming because first of all, the computer needs to calculate, find two prime number, big prime number. Then they have to multiply that. The multiplication is easy. But then they have to find the encryption and decryption, which is something power something. It's very difficult. So this trapdoor function, though this is a very good trapdoor function, this doesn't work much. This is still working till date. Most of the applications are using RSA, but it is evident that going forward, maybe 5 years, 10 years down the line, this is not a scalable solution. So we need to find out something else. The second best crypto system or second best asymmetric key cryptography is called the elliptic curve cryptography. Maybe in a coordinate geometry class, you have seen that this curve is the elliptic curve, and the equation for this curve is y square equals to x cube plus ax plus b. So if you just draw the equation, it will look like something like this. So this is called an ellipse, and this curve is called the elliptical curve. And it has a very nice trapdoor function. We can create. So now you understand that if I have a trapdoor function, we are fine. If we have a very good trapdoor function, we can create any crypto system. You're fine, right? For any asymmetric key cryptography, the biggest challenge is to get the trapdoor function. At least you have understood this part.
Yeah.
And what is the trapdoor function that is used for RSA? What is the trapdoor function? Phi. Yes, phi is the totem function is the trapdoor function. Here we'll use another nice thing. Just quickly, this will not take more than 5 minutes, and then we'll go for lunch. This is the elliptic curve. The equation is y square equals to x cube plus ax plus c. This is the equation, and this is the curve. This is how the curve looks like. Now I'm just taking a different color, maybe this one. There is something called a dot function. What is this dot function? Take any point of this curve, any point A. Actually, take any 2 point first. First, I'm explaining with any 2 point. Dot function is if you just draw a line with these two function, it will somewhere cross this curve. And let's take this one as a B. So if you just connect these two lines, it will cross some other point in this curve, which is C. Dot function says this extended, like any line will cross this curve 3 times exactly. So this one, and this one. So if you connect this one, it will connect somewhere. It will touch this curve somewhere here. And exactly the opposite of this one could be C dash. So C dash equals to A dot. So this point is A dot B. How we can get? Just connect these two. It will touch somewhere in the curve, and exactly the negative of this curve, as if you are sending a ball. Why we are calling it a dot? As if just we are playing a pool or a billiards, just a ball. This ball, if you connect, make a straight line from here, it just falls down. Tap, That it hits here. From here, it just falls down. So wherever it meets in curve,
Your
with curve.
screen is against Soumya.
No, I don't think so.
Yeah. No.
Okay, so this C dash is A dot B. Clear? So far it's clear. Now D equals to A dot C equals to A dot D. So we can actually keep the ball rolling from C. So this, if this is the dot function for this one. Again, what I will do, I will just connect these two dot, and it will connect somewhere here. So this will be A dot C, which is D. Again, from here, again I'm just touching A and D. It will again touch somewhere in this curve. So this one will be E. So if I keep on doing that, you can see we will get new and new points in this curve. Are we on the same track? I'm drawing the entire picture once again.
Yeah.
From A and B. So I am running a ball. Just it touch here and it comes here. So here it ends. Again, what I will do, I will just, I'm not stopping here. I will again, I'm connecting A and this number, this point. So it will again cross somewhere here. I'm not, so the dot function will somewhere here. So every time I'm connecting two line and then just going to the opposite direction. So again, I'm not stopping here. I am again connecting this one and A. So again, it will cross somewhere in the curve and it will fall somewhere. So if I keep on doing that, I will generate new and new points on the curve. The beauty of elliptic curve is that if I do not know how many times I am doing the rotation, I will never find where the point will be. That means this point I know only after 3 rotation I will reach this point. This point. I know only after 3 rotations I will come here. So I can do that. Well, I can keep on doing that for some 1,000 times, 2,000 times. But where we will end, we can never find it if we do not know how many times of rotation we have done. Make sense?
Yeah.
So this is the trapdoor function. We need to know how many times of rotation is happening. Otherwise, we cannot find the point. So this is a very nice trapdoor function. I'm giving you this curve, the equation of this curve. I'm giving you this equation of the curve. I'm giving you the initial starting point A. And I'm giving you the end point where I'm stopping last. Say this D. But if I do not tell you how many times I have rotated, sorry, I'm not giving you this D. I'm sorry. I'm not giving you this D. I'm giving you this curve and I'm giving you this A. But if I do not tell you how many times I have rotated, I can never reach this point D. I can never find unless I know how many times the rotation has done. So this how many times, this is the key. And the nice thing is that this key, of course, the how many times we are rotating is a very small one. It is just a number. And this is not a crazily big prime number or nothing like that. It's just any number. That many times I rotate, I will I will end at the decryption point. Simple. So if A is the encryption, like the message, start from this A, keep on rotating. And if I know that what is the key, if that many times I rotate, wherever I end, that is my decryption. Fine. Is it fine?
Yeah.
Yeah.
Okay. So this is elliptic curve. Elliptic curve doesn't look always this nice. Some elliptic curve. So instead, just you change the value of A and B, you will get different type of curve. A and B are two constants. If you change A and B, different values of A and B will give you different curves. So this is another curve. Y square equals to x cube minus 7x. This is a curve. This is also elliptic curve. This is another elliptic curve. So elliptic curve might be many of different types also, depending on the values of A and B. So these are the living legends. It's Shamir, RSA. These guys are RSA. Ron, Shamir, and Adelman. This is Markley, and these two guys are Diffie and Hillman. These are, in fact, if I'm not wrong, now also this week also there is a RSA conference, and these all of them are there in the RSA conference. Okay.
Yeah.
Usually, what we do? Okay. Well, what is the better encryption, RSA or AES or DES? Symmetric cryptography is better or acyclic cryptography is better? Tell me.
Based on the purpose.
Based on the purpose, okay. But what gives you the better security against confidentiality?
Confidentiality is RSA.
Asymmetric.
That is, AES or DES is far better than RSA. Is far better. Because in AES and DES, we are always doing like all these confusion, diffusion, all the mathematical properties that we have everything we have implemented there. But in RSA, this is just a trapdoor function. There is nothing substitution, no diffusion, nothing like that. Just a trapdoor function, and that is the base of the entire crypto system. If we break that trapdoor function, it is not even a one-way function. It is just a trapdoor function. That means it is difficult to break, but nobody says that it is impossible to break. And with a bigger computational power, it can anytime break. But AES and DES doesn't matter how much computational power you have, it is almost impossible to break unless you know certain information. So AES and DES, probably they are crypto resilient itself, because we never discuss about this symmetric key cryptography. We are never scared about the symmetric key cryptography when we have bigger computational power. We never do that because we know if we have a bigger computational power, we can increase the key size, and it will not make any overhead. It will almost seamlessly work. But for RSA, it's not possible. RSA is not that big. So RSA is a trapdoor function. It is everything based on the trapdoor function. It doesn't have any diffusion, confusion, nothing is there. So AES and DES are much better. So what we usually do, we use the RSA for exchange of the common key.
Exchange of the key.
First time we exchange the key, then everything will be sent with AES or 3DES. Then the problem, so only there will be one point of failure, one communication. If the first communication is broken for the RSA, then everything is broken. But if that is not broken, then we can think that rest of the communication is always secure, because that is done by AES or DES. AES and DES is much faster and much more secure. And
but by the time we change our AES key, we keep changing our symmetric key. So even if RSA is compromised,
we can
say
AES key, exactly.
After 1 hour, 2 hour, then our AES is already changed.
Exactly, that's happened. And for ECC key, 256 bit of ECC key is equivalent of 4096 bit of 4096 bit of RSA. So that is the difference. So just 256 bit is equivalent to 4096. So because this is just the number of rotation, it's a small number. We don't need any pi or any token function or nothing like that. Okay. So till now we understood the theory. Now we'll do some practical. OpenSSL, I believe everybody has installed OpenSSL. Now we'll do some hands-on.
In home laptop, I need to do.
Okay, if you
we did there, I guess, in that system.
Okay, if you do not have, then you can just run some cloud online OpenSSL tool. I'm just sending one link. You can use that. So if it is not installed on your system, at least you can get a Linux shell from this. Okay. Now let's take a break.
Okay.
The So like better you try to install OpenSSL. It works for on Windows or WSL or Linux anywhere. Or if you cannot do that, then use this link. This will give you a cloud Linux shell, but it will be active only for 30 minutes. And this is a very like it's only I think 512 KB of memory. I guess. So 512 MB of MB. Yeah, it's a very small computer. Better you can use it. You can install it on your laptop right away. It's not a very big tool. OpenSSL. Okay. Now, yeah. After coming back, we'll do some hands-on. We'll learn about PKI, and the rest of the things we'll cover. So I'm giving you 45 minutes of break. Not I've eaten 15 minutes of your